Next, we're going to tackle inference for the difference of means or proportions. So these are the kinds of questions we'll be able to answer. What is the difference between the proportion of women in excellent health and the proportion of men in excellent health? That would be a confidence interval. We're trying to estimate a number, the number being the difference in the proportions of the two groups that are in excellent health. A second one would be, is the proportion of women in poor health the same as the proportion of men in poor health? So this would be a hypothesis test for the difference of two proportions. Are those proportions the same? We can do the same two kinds of things for means. What is the difference between the mean height of men and the mean height of women? And is the mean age of adult women greater than the mean age of adult men? So those are the four kinds of questions we're going to want to be able to answer. And the theory is pretty much the same as it has been up until now. The sample statistics follow an approximately normal distribution. And so with the help of what we know about normal distribution theory and theories of what the standard errors of those sample statistics are, we can create confidence intervals and hypothesis testing. Here we'll just look at how to do this using our procedure template, but the theory behind the procedure is pretty much the same as it has been for the last few weeks. So let's look at this one. What is the difference between the proportion of women in excellent health and men in excellent health? So we'll go to our health data. We're interested in these two columns, health and gender. So in order to set it up and get it into StatKey, we will move the column general health over, move the column over. Then we'll go to StatKey, and use two categorical variables just to see what proportion of each are in excellent health. There are other ways of doing this, of course, including in Excel, but this is, I think, the easiest. So two categorical variables. So we put our data in here, and this is raw data. And let's look at the row proportions. So first of all, we have 478 men, and 0.236 of them are in excellent health. We have 522 women, and 0.245 of them. And so now we will go to StatKey. Now we'll go to our Excel template for two proportions. And we're doing a confidence interval. So the men, sample size was 478. For the women, it was 522. What were the proportions? Well, let's see, they were 0.236 and 0.245. 236, 0.245. One of the few mistakes you can make in using this template here is mixing the proportions and the sample sizes. So make sure you know which group goes with what. Population 1 is our men, and the sample size was 478 men, and 23.6% of them were in excellent health. And what do we get for our confidence interval? Negative 0.06 to 0.04. So what does this mean? That if you knew the proportion of all men who are in excellent health and the proportion of all women who are in excellent health, all adults in the United States, and subtracted those two proportions, you might get a number as low as negative 0.06 or as high as 0.04. In other words, if it was negative 0.06, that would mean that the 6 percentage points more of the women would be in excellent health, the men would be 0.06 less, and if it was 0.04, that would mean the men would actually be 0.04 more, even though in these samples the men are less. So we'll just copy those numbers. And this was a 95% confidence interval. we are 95% confident that the difference in the proportion of men in excellent health and the proportion of women in excellent health is between oh, that's interesting. Go ahead and copy for me. Negative 0.06 and 0.04. And notice, by the way, that the way I actually did it, putting men first, is different from the way in the different order than the question actually asked. If I wanted it, the difference between the women and the men, I would need to reverse these. Women could be 4% more, or, excuse me, women could be as much as 4% less or up to 6% more. So it's just a question of what order the question was asked in. Okay, so that's confidence intervals. Now, how about hypothesis testing? So we're not going to go through all of these. You would just use, obviously, the second half of this sheet to do hypothesis testing for two proportions. So let's not do that. Instead, let's go to means and do the hypothesis testing there, because the procedures are pretty much the same. It's just a question of whether you're talking about proportions or means. Okay, so what was our research question again? Is the mean age of adult women greater than the mean age of adult men? So let's go back to our health data. And now we will get rid of this column and put the ages there. And again, with the help of StatKey, we'll get the numbers we need. So copy these two. Go back to StatKey. And now we've got one categorical variable, gender, and one quantitative variable. So we put in our data, and look what we get. For the men, sample size 478, the mean was 45, standard deviation 17.6. For the women, 522, mean 45.797, standard deviation 17.05. So these two numbers are almost the same. It'll be very surprising if they turn out to be different, significantly different, and I'm sure they're not. And let's see if we can copy this so we don't have to look back and forth for the data. Okay, so we go in here. Oh, so first of all, if we're going to do a hypothesis test, let's state our null and alternative hypotheses. Our null hypothesis would be that the mean age of men is equal to the mean age for women The alternative would be that those two are not the same. Let's change that to not equal. It's not equal here because the question didn't ask anything about greater than or less than. Okay, and then how do we use our template to get the p-value? So can we still copy? Oops, no, we copied the wrong things. Okay, so let's go back here and see once again if we can copy our numbers so we don't have to flip back and forth between the screens. Maybe we can, maybe we can't. Oh, we can't. Okay, good. Okay, so for the men, we'll make population 1 the men again because they're in the first column. 478. Population 2, 522. Sample mean, 45.05. Sample mean, 45.8. Standard deviation, 17.62. Standard deviation, 17.05. And then we read the p-values down here. Now in our case, our alternative was not equal, so we're reading it from this line. We get a huge p-value, 0.495. So what does that mean? We do not have evidence that the mean ages of adult men and adult women are different. And then what's our rationale? If the mean ages of two populations were the same, there would be a 49.5% probability of getting sample means as far apart as we did. The observed data would not be surprising. So our intuition told us that this difference between 45.05 and 45.8 was not statistically significant, but intuition sometimes is wrong. And in fact, if the sample sizes had been much larger, then those differences would have been statistically significant. In fact, let's experiment with that. Suppose we'd gotten these same numbers, except the sample sizes were 4,780 and 5,220. Then suddenly the p-value becomes 0.03. So this difference between these two numbers, it's not statistically significant on small sample sizes, but for really big sample sizes, that would tell us that, yeah, women are a little bit older than men. So our hypothesis testing and confidence intervals for differences in means and proportions, the theory is very similar to the theory of what it was for one population proportion or one population mean, and the practice using our procedure template is pretty much the same.